I'm muted. Oh, thank you. Hello, can you guys hear me?
Yeah, we can hear you.
Okay, good. So I'm having technical difficulties today. So normally what I do is I like to use the Zoom on the lecture computer here, but it keeps freezing on me. But you know, it is 2:30, so I didn't want to waste any time. So I'm doing kind of a weird setup right now where I have the doc cam on, and I'm just going to lecture from here. And so I apologize that this recording probably not going to be good quality, but I will get to the bottom of the technical issues after today. Today's been kind of like a whirlwind of stuff going wrong because of everyone coming back to campus and everything. But you know, we'll make do with the best we can. So so thank you guys for your patience. And so for those of you in the classroom, welcome everybody. Welcome back to campus. So how's everybody doing today? Tired? Yeah. You guys good back there? Okay. All right. So so this is our first lecture back. I know it's not an ideal setup. I have this big ass computer monitor in the way. Let me go ahead and okay. Okay. All right. And so you know, I'm doing this kind of weird setup right now with the doc cam. I'm sitting here. It feels really weird, but you know, we're gonna make the best of it. Okay. And so the plan for today is we're gonna go ahead and continue on with our lecture notes on radial heat conduction systems. And so that's cylindrical systems, spherical systems, and everything like that. Okay. So before I get started, are there any questions I can answer on the homework or anything? I know I had quite a few people come to office hours this morning and ask questions on the homework. If you're on the Zoom, probably you have to turn on your microphone because I don't know if I can see the chat with this setup. Okay, all right. And so if there's no questions, let's go ahead and get started. Oh, question. The heat gradient. You mean the Fourier's law? The boundary condition. Okay. All right. So the question is, you know, to explain why the heat or the boundary condition at x equals to 0 is negative. And so basically, what we have is the, you know, let me go ahead and draw the full situation here. All right. And so this is problem 2 on the homework. Okay. You guys see okay? Or is there kind of a weird glare? I'm gonna move it up here. Okay, so in problem 2 on the homework, you know, we have basically a rectangular slot like this, okay? We have the length, this length here is L, okay? And on the left boundary, we have a heating type boundary condition. And so basically what I told you was that the, you know, we have a thin electric heater on that side of the plate, and it's heating it with the constant heat flux of Q naught double prime. Okay. And so if you're applying the boundary condition on the left-hand side, okay, we know that the way that we apply it is we apply Fourier's law. And so Fourier's law is going to be minus K dt dx. Okay. K times A, excuse me. And this is equal to the amount of heat that's being applied on that side, right? And so in order to get this into the form for the problem, we're going to divide both sides by A. And so we have minus K dt dx applied at x is equal to 0. This is equal to Q naught double prime divided by 2. And I divide by 2 because, you know, then because that plate's only receiving about half the heat that the heater is producing. Okay. All right. And so the question was, you know, why do we have this negative sign out here? And so that negative sign is to basically help us, or to basically fix our sign convention, so that we have a positive heat flow going from high temperature to low temperature, right? Because you know, if you evaluate this term, right, and so this term is always going to be, you know, temperature on the far end versus temperature on the near end, right? And so if we call this, you know, naively, we'll call this location 1, we'll call this location 2. The way that we evaluate this derivative is T2 minus T1, all divided by x2 minus x1, right? So this is kind of like a finite difference kind of approximation for that derivative, okay? And if we know that heat is going to be flowing from left to right this way, right? that means side 1 here is going to be at a higher temperature than side 2. Right. Okay. So in other words, we have T1 greater than T2, right? And so if we do T2 minus T1, right, so we're having a lower number minus a higher number, then this number is going to be just naturally negative, right? And so this negative out in front is just to kind of correct that, so that when we go from high temperature to low temperature, then we end up with a positive number for the heat flow. Yeah. Mm-hmm. Yeah. All right. Any other questions on the homework or anything before we get started? Yeah. Constant heat flux. Yes. What's that again? That equation is going to 0. So, so the double prime here it actually doesn't mean derivatives. That's a good observation though. So the double prime is just to indicate heat flux. Yeah. So in this class, if I'm going to give you a derivative, I'm going to write out the full dt dx kind of thing, because we use double primes to denote like heat fluxes or other stuff. So and so if you see primes or double primes, they don't mean derivatives. Yeah. Good. No, good question though, because I think it's the notation can get kind of confusing on especially between other classes and stuff. All right. Okay. And so I think we're good on questions. All right. So let's go ahead and pick up where we left off. Okay. And so we left off last week talking about heat, basically the heat equation in cylindrical systems. Okay. Okay. And so the biggest difference here is in the form of the heat equation, right? Because the ones that we're using for the homework and the ones that we talked about last week, we use Cartesian coordinates, right? And so that's x, y, and z basically. Although for our case it's only x. But for cylindrical systems, we have to switch to cylindrical coordinates. And so after we apply all of our assumptions, we end up with the following equation. Okay. And so we end up with the following differential equation. We have 1 over r, okay, d dr times kr dt dr, okay, is equal to 0. And so this right here is the cylindrical version of the 1D heat equation. And I think we were just in the middle of solving this in an example. Okay. Okay. And so, just because we kind of covered it at the end, let's go ahead and just do this example from scratch, just to make sure we're all on the same page. Okay. All right. And so in this example, we have a cylindrical system. Okay. In this case, it's a hollow cylinder. Okay. That's going to be the easiest case for us to solve first. All right, so yes, oh yeah, that's a good point. So in this equation right here, we've assumed that there's no generation, and so but normally there is a Q dot. Yeah, good question. All right, so this cylinder is going to have an inner radius and an outer radius, okay, and it's also going to have prescribed temperatures as well, okay. And so the inner surface is going to be held at temperature Ti, and the outer surface is going to be held at a temperature To. Okay. In addition to that, we know the thermal conductivity of the cylinder. Okay. And we're going to make the following assumptions. We're going to assume that that we have a steady state case. Next, we're going to assume that it's a 1D radial heat conduction. And so the heat is only just going to go radially outwards, just like that. Okay. 3, we're going to assume no generation. Right. And so since we're assuming that there's no generation or no thermal production, we can use the form of the equation that we have up above there. Okay. And that's it. Okay. All right, next we have the boundary conditions. And so the boundary conditions, we have prescribed temperatures on both sides. And so we have this is kind of the simplest case that we can have. And so we have T at Ri is equal to Ti. Okay. And then T at Ro is equal to To. Okay. All right. And so in this problem, what we're interested in is we're going to solve the heat equation. For the temperature distribution in the cylinder. Okay. All right. Any questions on the problem setup here? Yeah. Yeah. So most of the times, assuming no generation is usually a pretty good assumption, and so it would have to be kind of a special case where you have like some kind of you're solving it in a case where the material has some kind of chemical reaction going on, or the material itself is being heated by electric heaters all throughout. And so most of the time, assuming no generation is usually a good case. The problem will usually be pretty explicit if you cannot. And so they'll explicitly say that assume that there's generation, and then they'll give you the term for that. Yeah. Okay. All right. So let's go ahead and start with the heat equation. And so our heat equation under these assumptions is 1 divided by R, ddR, K times R, dt dr, all equal to 0. All right. And so we need to solve this equation for T. And so we're going to do this in a few steps. Right, so first thing we're going to do is we're going to multiply this entire equation by R. Okay, and so that's going to cancel out with this. And on the right hand side, we still have 0. So we have ddr of kr dt dr. Okay, is equal to 0. Right. So now we're faced with the derivative here. So we have ddr, and so we're going to take the integral of this. And so the integral dr is going to cancel out there. And so on the left-hand side, we're going to be left with kr dt dr is equal to integral of 0 is normally 0, but in this case, since we have a indefinite integral, we're going to add an arbitrary constant. Okay, so we're going to have c1 over there. Okay. Next, we're going to divide by k. We're going to divide by r. Oops. Okay. And so this kr is going to cancel out with this side. And on the right-hand side, we're going to have c1 divided by k r. Okay. I'm going to do, a little trick right here just to simplify our math. Since we know that C1 here is a constant, okay. We also have K here. So K here is also a constant, right? So K is the thermal conductivity of the material. Okay. And so what I'm going to do is I'm just going to kind of lump these two together because, We haven't specified a value for C1 yet. And so just to kind of make our life a little bit easier, I'm just going to combine them just so that we don't have to worry about two things floating around. In the end, it's not going to matter because when we solve for C1, it's going to take that value of K into account. Okay, so we're going to have C1 divided by R. Okay, so I'm basically just combining those two values. All right, so the next step, we're going to integrate this. Okay. All right, so once again, on the left-hand side, our dr is going to cancel out. And so on the left, we're left with just T of R, which is what we want. Okay. We have integral of C1 divided by R. And so that's going to be C1 ln of R. Okay. And then once again, since we have, we're integrating, we're doing an indefinite integral, we have to add an arbitrary constant on that side, C2. Okay. And so what we have here is our general solution. And so our general solution is C1 ln of R plus C2. Okay. All right. And so the next step is going to be to solve for these constants, right? And the way that we do that is going to be through the boundary conditions. Okay. All right. Any questions on this so far? Okay. All right. So let's go ahead and list out our boundary conditions, that we had at the start. All right. So our first boundary condition was T of R, I, right? So the temperature at the inner radius of the cylinder. This is going to be equal to Ti. Okay. Ti, which is given to us in the problem. Okay. And so if we plug in Ri into our general solution here, we have C1 ln of Ri plus C2. Right. Okay. And then we have the exact same thing for the other prescribed temperature. Okay. Okay. And so, before I move on, I want to make a note on the boundary conditions because I got a few questions on this on the homework. And so the boundary conditions that you apply here, right? I didn't just pull these out of my ass, but in this case I kind of did because I made up the example. But when you're applying boundary conditions or you're choosing boundary conditions to apply to your solution, they have to be the one that's given to you in the problem, right? And so when you're deciding what boundary conditions you want to apply, you have to look and see what conditions the problem actually gives you, and then use that as your boundary conditions. And so for the case on the homework, for problem 2 specifically, that one side is being heated by the electric heater, and so that's why you apply that boundary condition there. Whereas the other side is being cooled by convection, so that's why we use a convection boundary condition on the other side. In this case, we have prescribed temperatures, and so in this case it's pretty simple. But you have to kind of look at what the problem gives you, before you decide what boundary conditions you want to apply. Okay, so let's come back to this problem now. And so for this problem, we have these two equations, and we're going to need them to solve for the two unknowns, C1 and C2. Okay, and we're going to do the trick that we used at the end of the lecture last time, where we're going to subtract these two equations from each other. Okay, and so we're going to take the entire first equation and subtract the entire second one. Okay. And so on the left-hand side, what we're going to get is Ti minus To, right? Next, we have the C1 terms. We have C1 ln of Ri minus C1 ln of Ro. Okay. And then we have C2 minus C2. And so, because we have these two are the same in both equations, when we subtract them, they cancel out. which is really nice for us because, you know, now we don't have to worry about C2 and we can just solve for C1 just outright, okay? Okay. And so to simplify this, I'm going to apply one of the rules of logarithms, okay? And so since you know we have two logarithms here, so we have ln of Ri, okay, and we're subtracting another logarithm from that ln of Ro, you can actually combine these, right? And so basically the rule is if we have ln okay. If you have two logarithms that subtract each other, you can actually combine them into a single logarithm, but divide out its argument. And so we have ln of Ri divided by Ro. Okay. All right, and so if we apply that rule to our equation right here, we have C1 ln of Ri divided by Ro. Okay. And then we can simply take this term and then divide it out to the other side, and we can get our solution for C1. Okay. And so we have C1 is equal to Ti minus To divided by ln of Ri divided by Ro. Okay. Right, and that's our first constant solved. Right, any questions about how we obtained that that constant there? Okay. Okay, so that's C1, and so now let's go ahead and plug that back in to solve for C2. Okay. And so you can plug this in back into either of the equations. You know, it doesn't matter. You know, they both work. But for this case, but for my case, I'm going to plug it back into the second equation. Okay. And so I'm going to take the C1, plug it in right there. Okay. And so if we plug that in, what we get is To is equal to C1 here, which is Ti minus To divided by ln of Ri divided by Ro. Okay. This is multiplied by ln of Ro plus C2. Okay. All right. And now that we have it in this form, our only unknown left is C2, and so we can just go ahead and solve for that. And so if we subtract both sides by this this dude, then what we get is C2 is equal to To minus Ti minus To divided by ln of Ri divided by ln of Ro. Okay. ln of Ro. Okay. And now that we have both of our constants, we are ready to plug it back into our general equation and get the final answer for this problem. Okay. All right, so let's go ahead and plug it back in. And so if we plug it back into our equation, then what we get is T of R is equal to, we have C1, and so C1 is Ti minus To divided by ln of Ri divided by Ro. Okay. This is multiplied by ln of R. Okay. Then we have C2, right? And so C2 is plus To minus Ti minus To divided by ln of Ri divided by Ro. Okay. ln of Ro. Okay. Remember this guy right here. This is C1. And this guy right here, this is C2. Okay. And so all I did was I just plugged in C1, C2 back into our general equation. Okay. All right, so technically this is done. And so, you know, the problem asks you to solve for the temperature distribution, and here it is. Okay. but it's kind of still a little bit of a mess. And so let's go ahead and clean this up just a little bit. Okay. Okay. In particular, I'm going to clean up some of the logarithm terms. And so that's basically this term and this term, right? And so just like we had before, you know, we have a logarithm minus a logarithm, where the constant out in front is exactly the same, okay? And so if we combine those together, we get kind of the cleanest solution for this. Okay, so we have T of R is equal to Ti minus To divided by ln of Ri divided by Ro. Okay, ln. I'm going to combine these two logarithms, and so it's R divided by Ro. Okay, plus T naught. Bless you. Okay. And so that right there is our solution to this example. Okay. And so this is the temperature distribution in a hollow sphere, or excuse me, a hollow cylinder, where we have prescribed temperatures on the inner inner radius and the outer radius. Okay. All right. Any questions on this? Okay. All right, and so you know, that's just another kind of heat equation type problem. And so you know, this is very similar to problem 2 on your homework. You know, the biggest difference here is that we're starting out with the you know, with a different heat equation, because we're starting out with the you know, heat equation cylindrical coordinates. Okay, and so the next step that I want to do with this solution here is I want to compute the heat transfer rate through this in this temperature distribution. Remember, the equation that we use to compute heat transfer rate is Fourier's law. Oops. Okay. So Fourier's law, remember, is Q. And in this case, I'm going to do Q of Q sub R, okay, because it's going to be Q in the radial direction. This is equal to minus K times A, okay, times the derivative of T. Right? So we have dt dr. All right. And so since we're working in cylindrical coordinates, we can actually compute, or we can actually put in an expression for this A, right? And so what's the outer surface area of a cylinder? And so if we have kind of a cylindrical, you know, vessel like this, let's say its radius is R, right? Then the surface area of this will be the perimeter of the circle, right? And so we have 2 pi R multiplied by the length of the cylinder, right? Right? And so that's the surface area of the outer ring of the cylinder, right? And so this A right here, we can just go ahead and plug in that expression, right? We can do this because, you know, we know that we're in cylindrical geometries, and so we can come up with basically a more specific equation for that. Okay, and so we have QR is equal to minus K times 2 pi RL. Okay. And then we're going to multiply this by the derivative of our temperature solution. Okay. And so we're going to take our solution that we just computed, and we're going to plug it in here. Okay. And we're going to take the derivative of that with respect to R. Okay. All right. So let's go ahead and do that. And actually, you know, because we have this logarithm right here, it actually might be easier to compute it off this one, okay? And so if we look at our temperature distribution here, we can see a lot of it is actually just constants, right? And so we have TO, which is a constant. And we have everything right here, which is a constant too, right? So everything, everything that used to be C2 basically is just a constant. And so when we take the derivative, right, we take the derivative, then all these terms just simply go away because they're just constants, right? Because the derivative of a constant is just 0. And so the only thing we actually have to take the derivative of is ln of r, where the derivative ln of r is just 1 over r, right? And so if we keep that in mind, then this derivative term here is going to be ti minus to divided by ln ri divided by ro times 1 over r, okay? And so we have ti minus to divided by ln of ri divided by ro, okay, times 1 over r. Right? And so that I just plugged in, that's the derivative of the temperature distribution with respect to r. Okay. And so now that we have this expression, we can see that we have an r in the denominator, we have an r in the numerator here, and so those two are going to just cancel out. Okay. Okay. And so what we have is QR is equal to, and I'm going to rearrange this just a little bit. Okay, so we have minus k times 2 pi L, okay, divided by ln of Ri divided by Ro, okay. And then in the numerator here, we have Ti minus To. And so why did I do this? And so why did I, bother to separate it out like that? Let's look at the term here that I've boxed in green, right? And so that term that I boxed in green there has all constant values, right? And so it doesn't depend on r by itself, right? We have the inner radius and the outer radius, but these are just constant, and so those are kind of properties of the system. And so everything here is just a constant. Okay, and in fact, we can go even beyond this. It's comprised of constants that are properties of our geometry. Okay. Right. And so we have a lot of factors here, like the radii, right? Those are properties of our cylinder. We have the length of the cylinder, and so that's obviously a property of our cylinder. And we also have the thermal conductivity, right? And so thermal conductivity is the is a property of the material of our geometry. Okay. And then we have 2 pi. 2 pi is just chilling, and so 2 pi is always going to be the same no matter what. And so we can actually give this another name, okay, a familiar name, and so one that we've seen in Cartesian systems. Okay. And so these constants right here, when combined together, this is actually defined as the thermal resistance of cylindrical systems. Okay. Because remember, whenever this whole idea of thermal resistance is that, if we draw a circuit, right? Right, where the endpoints of our circuit are our 2 end temperatures. And so in this case, we have the inner temperature and the outer temperature, right? And we want to compute the amount of heat that transfers from, let's say we go into out, okay? Because remember, one thing we've talked about in this class is that as long as there's a temperature difference between 2 points, then there's going to be some heat transfer, right? If we want to compute what this is, right, we can just use our thermal circuit, right? Where this resistance is going to be the value of this resistor right here, okay? And so if we take the temperature difference, we divide it by the thermal resistance between them, then that's going to give us the amount of heat transfer, okay? The only question when using this problem is, what expression do we fill in for this R cylinder, okay? And so that R cylinder is going to be, what I have up there, right? And so if we kind of connect these two concepts, our equation for R cylinder, right, is going to be the inverse of this guy right here, right? We also have a negative, oops. We also have a negative out here, and so we have to apply that negative throughout. Okay? And so I'm going to use that negative to flip the sign of the logarithms. Okay. And so our formula for the thermal resistance of a cylinder is the natural logarithm of RO divided by RI divided by 2 pi K L. Okay. And so if you have a cylindrical system and you want to compute the amount of heat transfer that goes through it, you can use that equation right there for the resistance. Okay. And in the next homework 2, which I'm working on right now, I'll probably get it out to you on Wednesday after the first one's due. You'll have a problem that deals with this. Okay. All right. Any questions on how we got this formula for thermal resistance? Okay. All right. I think I have an example later with thermal resistance, but before we get that, I want to do another heat equation example because there's an interesting case which can happen in cylindrical systems that you don't have in Cartesian. Yeah. And so this is going to be another heat equation example because it's interesting. And so this is going to be a temperature distribution problem. Okay. And so we're going to compute the temperature distribution okay. And we're going to do this for a solid cylinder. I know it doesn't seem exciting, but trust me, it is actually more interesting. Right? And so we've done a hollow cylinder, and so now we're going to do a solid. Okay. Solid cylinder. All that means is that the entire cylinder is is solid, and so there's no inner radius, outer radius. We just have radius. Okay. And so we'll call that RO, and I'll keep things simple. And so let's say that for our boundary condition, we can assume that we know the temperature at the radius of the cylinder. Okay. All right. Assumptions. Okay. And so our assumptions are going to be mostly the same as before. Okay. So we have 1D radial. 2, we have steady state. 3, we're going to assume no generation. Okay. And that's it. All right. So before we start solving it, let's go ahead and write out our boundary conditions. Okay. And so our boundary conditions, it's pretty straightforward. And so you can see here we have a prescribed temperature at the radius, right? And so we have T of RO is equal to TO. Okay. So that one's pretty straightforward. but we need another boundary condition, right? Because when we solve the heat equation, we're going to have two unknown constants, and so we're going to need two boundary conditions to solve for those constants. But right now we only have one, right? So we only have just the one boundary condition. TRO is equal to TO. Okay. And so we're going to need another one in here, in order for us to solve for it. Okay. But I'm not going to tell you it just yet, because I think it's more meaningful, to reveal it once we get there. But it's kind of surprising what it is. Okay. All right, and so since we're assuming no generation, we can start our solution at the same point that we did last time, right? And so we have 1 over r, okay, times ddr of kr dt dr is equal to 0. Okay. And I'll write out all the steps, but I'll just kind of go through it real quickly, just because this is kind of a repeat of what we did last time. Okay. And so I'm just going to go ahead and just write it down, and and you can just kind of follow along there. So I'm going to multiply both sides by r. Actually, I'm going to do r over k, because this k is a constant. Okay. And so we have d dr of r dt dr is equal to 0. Okay. We integrate to get rid of this ddr. So we have r dt dr is equal to c1. Okay. Divide both sides by r. We have dt dr is equal to c1 over r. We integrate one more time. We have t of r is equal to c1 ln of r plus c2. So up to this point, it's exactly the same as our previous example. And so, that's why I kind of flew through it. But in the end, we get the same general solution here. Okay. And so our general solution is C1 ln of R plus C2. Okay. Okay. And so now we're faced with the exact same task as our last example. Okay. And so we have to solve for C1 and C2 using our boundary conditions. Okay. All right, so let's apply our first boundary condition first. And so our first boundary condition was T at RO, okay, is equal to TO. Okay, so this is ln of C1 ln of RO plus C2. Okay. Okay, so that's good. That's fine. And so now we have the second boundary condition, right? Because right now we don't have enough information in order for us to solve for both C1 and C2. Okay. And so for the second boundary condition, let's look back at our domain. Okay. And let's think about what's unique about this domain compared to our last example. Right? Okay. And so in this problem, we have a solid cylinder. That's kind of like little baby hair right there. Okay. And let's think about the middle of the cylinder. Okay. Right. Middle of the cylinder being r is equal to 0. Right. For a solid cylinder like this, and this is going to be true for a solid sphere, once we get there as well, r is equal to 0 is actually a valid part of our domain. If you think about the hollow cylinder that we had before, that wasn't the case, right? And so r is equal to 0 is here, right? But that wasn't part of our domain, because our domain stopped at the inner radius, right? Right, so that was our domain in the previous one. And so in the hollow cylinder, our domain stopped at Ri. And so in our previous example, we didn't have to worry about what was going on at the middle of the cylinder, just because it wasn't part of our domain. Okay, but now we do, because it is part of our domain. And so our solution has to be valid at r is equal to 0. Okay. Let's look at our general solution again. Okay. If we look at our solution, and if we plug in r is equal to 0, then every term here has to be valid, right? And so let's plug in r is equal to 0 for this one, right? And so we have C1 ln of 0. Okay. What's the natural logarithm of 0? It's so everyone I always forget this one too. So if you graph the natural logarithm, okay, we'll call this ln of x. Right? I think the one that everyone remembers is 1, right? And so when you take ln of 1, it equals 0, right? And that's true. And so if you graph natural logarithm from here, it looks kind of something like this. But as you approach 0, it kind of does this. Okay. And so the natural logarithm of 0 is actually minus infinity, if you can even call it that. Right? It's actually like undefined, but we call it minus infinity just to give it some kind of intuition. Okay. Right. And so we kind of have a problem here, right? And so, if r is equal to 0 is part of our domain, and our solution has to be valid at the center of the cylinder, we have a problem, because if we plug in 0 here, then we get minus infinity, right? And I know maybe not a lot of people have physically felt this, because it's impossible, but if you touch the center of a cylinder, right? If you touch this of any cylinder, like a piece of chalk, right? If you touch the center of that piece of chalk, I guarantee you it's not going to be minus infinity temperature, right? It's kind of a Schrodinger's box kind of thing, where you can't, as soon as you cut it open, it's not the middle anymore. But trust me, it's not minus infinity. Okay. And so in order for our solution to be valid, we have kind of a paradox here. We have one term here that can't be valid at r is equal to 0. Okay. And so what do we do about this? And so what we do, just like all the problems in my life, we'll just pretend it doesn't exist. Okay. Okay. And so what we say is that, in order for a solution to be valid, you can't be here. Okay. Okay. And so we literally just Thanos snap it out of existence. Okay. And so that's actually our other boundary condition. Okay. And so the other boundary condition, whenever you have a solid cylinder or a solid sphere, or I can be a bit more general. And so when the center of radial system let me just kind of get rid of this for now, is part of the domain, okay, then the one boundary condition is, okay, and so the other boundary condition that we have is the solution must be valid at the center. Okay. Right, and so if we apply that boundary condition to our temperature solution, okay, that means that the C1 term cannot exist. Okay. Okay. You can say that, you know, we're going to set C1 equal to 0. You know, and mathematically that gives you the exact same thing. That term just goes away. And honestly, that's kind of how I thought about it for many years. But but after thinking about it some more, you know, it's even beyond that. Like that term just physically just can't even exist for terms like this. Okay. And so our, you know, if we say the C1 term can exist, then our temperature solution, T of R, is only equal to C2, right? And so we have one constant left. And so if we apply our first boundary condition, which is the temperature at the exterior of the cylinder, okay, remember T of, T at RO is equal to TO, okay? And we set that equal to our general solution here, which is just C2, okay? We get C2 is just equal to TO, okay? And so our final temperature distribution is a constant temperature. Okay? And so we have T of R is just simply equal to TO. Okay. So kind of a boring solution. And so, you know, we have just a one-term constant solution. But, you know, I think the path to get here was kind of interesting. You know, we mathematically got rid of one of the terms in our solution. Any questions on this? Yeah. And so, so the question is, you know, if we were to solve this question with numbers, you know, would the solution just be, you know, the temperature at the outer reads? That's if it's given to you in the problem. And so in this case, you know, we were given that the outer temperature was TO, and so we know that's all the way there. But you know, I might give you a case where there's convection cooling on the outside, or maybe there's some heating coming in from the outside, like you're surrounded by a thin heater, and so you're going to have to adjust based on the boundary conditions. Okay. All right, and so let's go ahead and move on then. And so I actually have one more heat equation example in the notes, but you know, I did want to start spherical stuff today, and so I'm going to go ahead and skip through that. But just know that in the notes, in the lecture notes that I posted, there is one more example for heat equation cylindrical coordinates, and that one's a good one to look at too, because the boundary conditions are more complex, and so you'll get to see convection and you'll get to see you know, heating as well. But I did want to show you how to use resistors, and I did want to show you know, one interesting concept about what's called a critical thickness. So I want to make sure I get through that today. Okay. All right, and so this example here, we're going to look at thermal resistances in cylindrical coordinates. Okay? And I'll basically show you how to set it up, and then that'll kind of be the precursor of kind of the next topic. Okay. All right. And so, you know, thermal resistances are a great tool for us to use in cylindrical systems, and they're particularly very useful for composite type materials. And so, you know, if you think of problem 3 on the last homework, you know, that was a composite system where I gave you multiple layers of solids with, you know, some layers of fluids in between. And so circuits are really great for that because you can just use a thermal resistance to represent each of the thermal properties of each layer. Okay. And so we can do that in cylindrical coordinates too. You know, and again, they're great for layers or situations you have multiple layers of material. Okay? And so let's look at a situation. Okay. Let's do one more. Okay. Let's say that we have 3 layers of solids. Okay. And so let's say that we have this is a solid layer right here. So this is K1. Okay. And then we have another layer on top of that K2, and we have another layer on top of that K3. Okay. Right. We can label all of the radii here. Okay. And so let's say the innermost radius, we'll call it R1. The second radius is R2. The third radius is R3. And the outermost radius is R4. Right. And some additional parameters, because why the hell not? Let's say we have some convection cooling, both on the inside and the outside. Okay. And so on the inside, let's say we have like an inner flow. So let's say we have some kind of pipe flow on the inside, and so this is going to have a inner temperature of T infinity I, and a convection coefficient of HI. Okay. And on the outside, we're going to have air that's blowing over it as well. Okay, and so that's going to have a ambient temperature TO, or T infinity O, as well as convection coefficient HO. Okay. And so since this figure is kind of a little bit messy, I'm going to go ahead and draw it in another form. Okay. Draw it kind of like in pound cake form here. Okay. And so this is kind of like a slice of this material right here. Okay. Just to make things a little bit easier to see. Okay, so we have K1, K2, K3, okay? We have our radii, we have R1, R2, R3, R4, okay? And then we have our fluids flowing. It's on the inside, we have T infinity I and HI, okay? And on the outside, we have T infinity O and HO. So the figure on the right is just another representation of what we have on the left there. Okay. And so we can go ahead and give this a story. Okay. And so let's say that we have a very common situation is let's say that we have a very hot liquid that's flowing on the inside, right? And so let's say that the liquid on the inside, let's say that this pipe is transporting some very hot oil. Okay. Okay. Normally, in situations like this where you're transporting a very dangerous liquid or a very hot liquid, then you're going to build layers of insulation on the pipe. So you're not just going to have a straight up pipe. You're going to have different layers of insulation on that, so people can touch that and not burn themselves. Okay. And so each of these different layers here represents, maybe a different layer of insulation, that goes on the pipe to make it safe. Right? And on the outside, we have, we say that, let's say that this room is air conditioned cooled, and so this is just simply the air conditions on the outside. Okay. And so it's very common in situations like this, to want to compute, how much heat loss do we have in the pipe. Okay. Great. Because, just like any heat transfer situation, if we have T infinity I, and if that's greater than T infinity O, right, then naturally heat is going to go that way, right? And so heat's always going to go from the high temperature to the low temperature. And so in order to perform, the thermal design of the system, you have to compute, how much heat are we going to lose in this situation, okay? Okay. And so, in situations like this, you can do it with the heat equation, of course, but you'll probably hate yourself because there's so many different layers here. And so the easier way to do this is with a thermal circuit, right? Okay. And the way we're going to use the thermal circuit is that each of the different layers that we have is going to be a different resistor. Okay. Okay. And remember, we need to count the convection layers too. Okay. Okay. All right, and so let's go ahead and write out the thermal circuit for this. Okay. And so you can see here we're going to have 5 resistors, right? And so we're going to have two, one resistor for the inner convection, one resistor for the outer convection, and then 3 insulation layers. And so that's 3 more resistances. Okay. And so, we're going to have T infinity I on one end of the circuit. Okay. Right. Then we have our 5 resistors, and then we have T infinity O. Right. And so heat's going to move from left to right. Okay. And so we're going to need to compute, what each of these resistors in the middle are. Okay. Okay. And so we know the first and last resistors here are going to be convection resistances because those are resistances that are connected to the airflow. Okay. Okay. Whereas the 3 middle resistors, this corresponds to the 3 insulation layers of the material, and so those will be conduction resistances. Okay, all right. So let's actually write out what these expressions are. Okay. All right. So our convection resistance, remember, is just going to be 1 divided by the convection coefficient multiplied by the area. And so for the inner one, for the inner convection resistance, we're going to have 1 divided by HI multiplied by A. Okay. And then for the outer one, we're going to have 1 divided by HO multiplied by A. Okay. And in fact, this will be the inner area and the outer area, because what you'll see is that they're actually different. Okay. Yeah.
Is there a reason we don't take into account the radius for the inner convection?
We do actually. So that's actually kind of the next point. That's a great question. And so the question is, is there a reason we don't take into account the inner radius for convection? And so the way that it actually gets factored in is in this cross section area. Because remember, for cylindrical systems, we actually have a formula for the surface area here. Right. And so remember, the way that we compute surface area is we take the perimeter of the circle. And so in this case, since we're doing the convection for the inner radius here, we're going to do 2 pi times the innermost radius, which is R1, okay, multiplied by L, which is the length of the pipe. Assume that I gave you the length of the pipe. I'm not sure if I said it yet, but we can assume that we know it. Okay. And then we can do the same thing for the outer surface area too. Okay. And so this is going to be 2 pi times. Since this is cooling the outermost layer, we need the outermost radius for this, and so this is going to be R4, okay, times L. And so those are, the two expressions for the 2 convection resistances. Okay. And so very similar to our planar convection, except now we actually plug in an expression for the area. Okay. Because our area is defined by the radius. Okay. And so those are the convection resistances. Now let's do the conduction ones. Okay. And so if you remember, our conduction resistance for a cylindrical system is ln. Ln of the outer radius divided by the inner one. And so for the first layer here, if we consider just this layer right here of K1, right? The outer radius for this one is actually R2, right? And the inner one is R1. So we're going to do ln of R2 divided by R1, okay? Divided by 2 pi times the thermal conductivity of that layer, which is K1 times L, okay? Right, same thing for the second insulation layer. And so the second insulation layer will be ln of R3 divided by R2, okay? And then divided by 2 pi K2L. And the third conduction layer will be ln of R4 divided by R3 divided by 2 pi K3L. Okay. All right. And so, presumably, if you have all of these parameters, and so you have all the radii, you're given all the thermal conductivities, you're given the convection coefficients, you can just plug in and solve for numbers for all of these terms here. Okay. And then all you have to do, right? So since we're interested in the heat loss, what we can do is we can use our circuit. And so we can use T infinity I minus T infinity O. This is going to be divided by the total resistance. Okay? And remember, the total resistance, the way you get that is you just simply add up all the resistances that you have over there. Okay. All right. Any questions on this?
So we can't just divide up area.
Exactly right. So in this case, the area is actually constantly changing. So if you compare the surface area right here, that was weird. If you compare the surface area right here, right, and so you have a cylinder of a certain radius, and you compare that to the surface area on the outside of that, the surface area is actually going to grow, right? Because if you have a cylinder with a larger radius, then your surface area is actually going to be growing. So that's actually a very unique characteristic of cylindrical systems, is that our surface area, is going to be different as we flow from one radius to another one. And it's actually the topic of what I want to cover next too. So that's another great segue. So you guys are asking good questions today. But what you can do for cylindrical systems is that instead of A everywhere, what you actually have is L everywhere, right? So all these expressions have a length. And so what you can do is you can actually divide by that L and get a heat transfer per unit length. So that's another thing that you can do in these systems, and that's quite common, especially if you are designing like an installation for an electrical wire. A lot of times you're interested in per 1 meter or per 10 meters of this installation, how much heat loss am I going to have from this installation? Yeah, actually, I believe the homework problem does that as well. But that's homework 2. That's the next one. All right. Any other questions on this example here? Okay. Okay. And so there's one more topic I want to go over. I don't think we'll have time to finish it, but I'll go ahead and introduce it. And it actually has to do with that exact fact that as we increase the radius, we actually are changing surface areas. Okay. Okay. And so that's unique. And so, that's something that we didn't have, in planar systems. And so to kind of illustrate kind of a really interesting case, let me give you kind of a simple case study. And so let's say that we have a cylinder. It's going to be a hollow cylinder. Okay. And we have an inner radius and an outer radius. Let's say that we know the inner temperature, okay? And so the inner temperature is going to be Ti, okay? But on the outside, we actually have convection cooling. So let's say it's air, we have air cooling, okay? And so that air cooling is going to have an ambient temperature T infinity and a convection coefficient H, okay? All right. So fairly simple system, right? And so we have two layers. And so we have the conduction of this layer. Let's assume we know the thermal conductivity, and we have convection cooling on the outside. Okay. Let's take the situation and let's say that we want to modify it, right? And so let's say that you're engineering the system, it's very similar to the last example where you have kind of a very hot liquid on the inside and you want to insulate it, from the outside. And so kind of the instinctual thing that you want to do is, someone tells you, I want to add insulation to this, I want to make it more insulated. You're going to make the insulation thicker, right? Okay. And so in other words, if we make the insulation thicker, that would be the same thing as increasing RO while keeping RI the same. Okay. And so in other words, we're just going to add, additional layers of insulation on top. Okay. What we expect, and probably what we want to happen, is we want the overall thermal resistance to increase. Okay. Right? Because we're adding insulation, and so we expect, more insulation means more thermal resistance. Okay. Right? But of course, because I'm posing it to you in that way, we have to ask, but does it really? So does it actually increase the thermal resistance? Okay. All right. It's an interesting thought experiment, right? Because that's kind of the natural thing you want to do. You want to add some thermal resistance or thermal insulation in order to, increase that thermal resistance. Okay. All right. And so when you actually do that, and so when you add insulation to this, two things are actually going to happen. On the one hand, we are going to get the exact same effect that we want, right? And so if we add insulation thickness to this, then one way that we can say is that the conduction resistance of the pipe or the insulation is going to increase. Okay. Okay. Remember our formula for conduction resistance, right? And so it's ln of RO divided by Ri divided by 2 pi KL, right? Right. And so if we increase RO, right, we have RO here in the numerator of this expression. And so if we increase RO, then our conduction is going to increase. And so the formula supports this, right? It only increases at a rate of natural logarithm, but it's still an increase. Okay. I kind of put the color, but it's okay. All right. So that's the natural thing that you think would occur. Okay. The other thing that's occurring at the same time, right? Now remember, the other aspect of this problem is that we have convection that's occurring on the outside. And so the other thing that's occurring is that the convection resistance is actually going down. Okay. And why is that? Oops. Remember from the last example what our formula for convection resistance is, okay? Okay. right? If we look at the formula for the convection resistance, you can see that RO is actually in the denominator, right? And so if we increase RO, then it's going to cause our convection to go down. And the main reason this is happening is by increasing the RO here, we're also increasing the outer surface area of the cylinder. Okay, and by increasing the amount of surface area, you're actually reducing the convection resistance. Okay, and so both of these are happening at the same time. And so unfortunately, we are out of time today, and so I don't have time to go through the math. But on Wednesday, when we pick this up, I'll show you a formula which you can use to find what's called the critical thickness, and that's actually the thickness where the thermal resistance is at its minimum. Okay. All right, and so I did go over time, so I apologize for that. So thank you guys for sticking around. If you have any questions about today's lecture, I'll be sticking around for a bit. But if not, I'll see you on Wednesday. And thanks for being patient with my technical difficulties too. I'm hoping we don't have to do this on Wednesday with more proper setup.
Are you using Dr. Lee's tablet?
Wait a second.
Are you using Dr. Lee's tablet?
I am, because something that happened this morning was I lost my stylus, and so I was scrambling trying to find a new one that works with my iPad, but I couldn't, and so Dr. Lee lent me his.
Oh, okay.
Yeah, but I'm gonna give it back to him. I'm gonna get a new one after this lecture. Yeah. Hey, what's up?
Oh,
Oh, nice.
so actually wanted to ask you something about if you could kind of look at homework.
Sure. What's up?
Australia. It's kind of I kind of want to work through like two.
Okay.
But I don't think it's right.
Okay.
So I went ahead, just put down all the assumptions I could write down the notes.
Okay.
And then here's the thing, I've had two different boundary conditions for these. So I did
Okay.
constant heat flux.
Yep.
And I also did them with convection surface.
No, that's right. Yep.
So here's my question. I'm not sure where I got the answer. I saw somewhere here where you made about the Q, the heat flux. Yeah, there's more of the heat transfer rate equal to 0. I'm not sure. And that's what I was asking about earlier. That's
I
if
see,
you drain it from because that's exactly what I did. I made it equal to 0 when I had to divide it out. And I ended up getting Q double prime O over 2K. Obviously the Q over 2 was from what you gave us, but is that still right? Because I'm getting the right answer.
So the one that we did in the lecture was a special case, and so that's when you have what's called an insulated surface. And so when you have an insulated surface, then you set the entire thing equal to 0. But here we don't have an insulated surface. What we have is it's being heated by a heater. And so instead of equal to 0, you set it equal to whatever the heating rate is. And so actually, if you got the right answer, I'm going to see this again.
Yeah, just go ahead and thread that up. And then I did this. And I got that from my C1.
Okay. So this boundary condition, because it's applied on the left side, we're actually applying it at x equals to 0, not x equals to 0. And so you can see here that you're applying it at x equals L. You would actually apply it at x equals to 0.
Okay, so then that shifts to wait. It wouldn't because gotcha. Yeah. Also, question. I barely pass by the circuits behind it.
So I said circuits, but it's, you know, you kind of just need kind of a very basic level of it. So you set it up really good. So you can see here that we have all these resistances here. And so you have a conduction resistance, conduction, 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 conduction. That's perfect. And so the next step in this problem is actually to use the circuit to compute the heat transfer rate. Okay. And so how you do that is you have a temperature on this side. You have a temperature on this side. So I believe this is a outer. Yeah. And so what you're going to do is you're going to do T0 divided by T infinity. You're going to divide it by the total resistance, right? And that's going to be equal to.
And we're solving for the Q,
So in this problem, actually, I give you the Q. So I give you a little bit of a mix up in this.
right. I see on other problems that you also had different added Qs. For example, like the film project problem that we did.
Yeah.
You added the Q air plus the Q of the not the film but the substrate.
Yeah.
We don't have a substrate in this film, but so we just rely on the Q that you gave us, or
So the in-class example is interesting because the Q is actually being inserted kind of at the middle. And so here we actually have the Q coming from this side. So the heat is going this way. And so you don't have to worry about any splitting. So there's just going to be one Q that.
but there's there's gaps in the along the plates.
Yes. So those gaps are the air. So you have the convection.
Gotcha. Okay, that makes sense.
Yeah. And so since I give you Q in this problem, the only thing that's unknown here is. And so you're going to set up the equation for Q. So you're going to have Q equals PO minus Q infinity divided by R total. And then since I give you Q, the only unknown in that equation is actually going to be the current.
Are you still alive?
Yeah, let me just go ahead and leave.